So by definition, this is all about strong acids and bases on page 89. Strong acids and bases, what do we know about them? What do they do in water? 100% ionizes in water. Yes. So if you have an H, say on HCl, 100% of it ends up dissociated. Yes? And how much do we have left of the HCl stuck together? 0%. Okay. So if we look and we say, what is the hydrogen ion concentration in 1.5 molar HCl, what we can do is if we write our dissociation equation, underneath the HCl, we can write 1.5 molar. Now, I have a tendency to put it in brackets. It's not incorrect if you don't, but I like to put it in brackets because it reminds me how much is actually left as HCl stuck together. How much? None. None is left as HCl stuck together, which is why I put it in brackets, just to kind of remind myself that I don't actually have any HCl stuck together. Okay? But what it does mean is because we have coefficients of 1 to 1 to 1, every one HCl that dissociates, we get 1 H plus, and every one HCl that dissociates, we get 1 Cl minus. So the concentration of H plus then is 1.5 molar, and the concentration of Cl minus is 1.5 molar. Okay? And this is one way of showing the work for a strong acid or a strong base, is just to write the dissociation and write the numbers underneath and just use the mole ratio to get the values. Okay, so that's one way of showing your work. So therefore, your hydrogen ion concentration is 1.5 molar. Or you can even just do that in your head if you're not asked to show any work. Okay? Easy. But sometimes the question might not say, what is the H plus concentration? Sometimes it might say, what is the OH minus concentration in a 1.5 molar solution of HCl? And sometimes that'll throw people for a loop because they're like, hang on, ho, 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 ho. Contains H, it contains Cl. Concentration of OH is 0 because there's no OH. Except that this all takes place in aqueous solution. So who is always present? Water. And what does water do? It auto-ionizes, dissociates into H plus and OH minus. Not very much, but there's always going to be at least a little bit of OH minus, even if you have some H plus. So you could find OH minus using one of our tools in our toolkit that we've learned in the last couple days. You can find OH minus using Kw equals H plus times OH minus. Okay, so I can say, what is the hydroxide concentration in this acid? And you find the hydrogen, and then you can find hydroxide. I could also say, what's the hydrogen ion concentration in a base? You would find the hydroxide, and then use Kw to find the hydrogen. Okay? The other thing we can do, we can use, we can find our pH using pH equals negative log of H. You could also find pOH if you had to. It would just be a couple of steps. Okay? All right, here we have another question. What is the hydroxide in 0.030 molar barium hydroxide? What type of substance is barium hydroxide? It's a base, and it is a strong base because it is a metal hydroxide. For the purposes of this unit, they are all strong bases. Like I said, in our next unit, solubility, we're going to worry about whether it dissolves completely or not, but we're not going to worry about that for this unit, okay? So, because it is a strong base, that means it goes to completion. Okay, so when we draw our arrow, it's going to go just one way. And the thing that's different about this one is that we have this little 2 down at the bottom of OH. So every time it dissociates, we don't just get one hydroxide, we get 2 hydroxides. So when we write our concentrations underneath, 0.030 molar is the concentration of the barium hydroxide. Barium, it's a 1-to-1 ratio. So we get 0.03 molar. But when it comes to OH, do we get 0.03? No, we get twice as much. So we get 0.06 because of that little 2 there. Okay, so that's one way that you can show your work for that. Therefore, concentration of OH is 0.060 molar. Could you find H plus?
Yes.
Yes. Could you find POH? Could you find pH? Yes. And if you said no to any of those questions in your head, then you will want to drop by during Flex tomorrow or the next day, okay? And make sure that you've settled that. All right, so if I said to you, we've got hydroxide is 0.06, and I said, could you find H? And you in your little head said, oh, no, I couldn't. Come by and see me, okay? So the moral of the story is when you have a strong acid or a strong base, you simply write the dissociation. You use the mole ratio to find concentration of H plus if it's an acid, concentration of OH minus if it's a base. And then we use the normal tools to convert into whatever is being asked for in the question. What the heck are these normal tools? Tell your partner what you think the normal tools might be. They're the ones we learned in the last few days. What's one of our normal tools? KW is equal to H times OH. What's another one? PKW is equal to pH plus pOH. Good. And pH, I'm actually just going to call it px because there's pH and pOH. Px is equal to the negative log of x. So that could be H or it could be OH. Okay, so you've got those ones. And you could also have, if you really needed to, you could have that the concentration of X is equal to 10 to the negative P of X. Yes? Okay. Anyway, they're all written here. There's a bunch of exercises here. We're not going to do them though today, okay? Because we're going to keep moving because we want to get through this unit so it can go on to report card number 1 for this term. Okay, so here we go. We've just done strong acids. Now we are going to do weak acids. And with a weak acid, they form an equilibrium. And therefore, if something forms an equilibrium, what kind of a value will it have? It will have a KEQ. And what do we call a KEQ for a weak acid? Ka. Yes, indeed. Okay. Now, if you remember back in our equilibrium unit, which wasn't that long ago, when we were given initial conditions and equilibrium conditions, what kind of a table did we need to use? We needed to use a Rice table, which, what did the R stand for? Reaction. I stood for the initial concentration. C stood for change in concentration. And E stood for equilibrium concentration. Okay, so we used a Rice table. We're going to need to use a Rice table and a Ka anytime we have a weak acid. Now, in order to help you remember this, if you have a weak acid, so if you have a weak acid, imagine you have a weak little old lady. She's walking along carrying a bag of rice. So what does that mean? It means you need to use a Rice table. Yes? She's so weak, poor little old lady, that she drops the rice and the crows come along and eat it. And what do they cry out while they're eating it? Caw, caw. Yes? Ka. Ka, caw. Okay. So hopefully that's going to remind you that when your acid is weak, you need to use a Rice table and Ka. All right, so remember, for a weak acid, use Rice table and Ka. I'm quite proud of that little graphic there. I just took lots of images and stuck them together. I didn't draw any of it because I can't draw, but anyway. All right, so remember what we just did a moment ago. What kind of an acid is HCl? Strong. It's strong. And if it's strong, do you need to use a Rice and Ka? No, you just dissociate it and you say, oh, I've got a 1:1:1 ratio, and you're done. Okay, so it's really important anytime you get a question, you ask yourself, is it strong or is it weak? Okay. Here, we're going to be dealing with weak acids for the rest of this, which require Rice and Ka. So we are asked, what is the concentration of H plus in 0.50 molar CH3COOH solution? So anytime you see an acid, what should you ask yourself? Is it strong or weak? So go look on your table and decide, is it strong or weak? And we go to our table and we say CH3COOH. There we are. Oh, it's in the middle of the table. It is weak. And if it is weak, then you say to yourself, I need to use Rice table. And I need to use Ka. So it's a weak acid. It will not dissociate completely. You will set up an equilibrium. So make sure you use an equilibrium arrow. And writing that is worth 0.5 marks. Okay, it should be part of your Rice table. Yes? This little thing here, 0.5 marks. Now, we look on our chart and we can find that Ka for CH3COOH is 1.8 times 10 to the minus 5. So that's a piece of useful information that you can take back with you to the question. Okay. You also get marks for writing the Ka expression. So you should write Ka equals, and then you write the products, which are the H plus and the CH3COO minus over the reactants. And guess what? You get a half a mark for writing that too. You don't even need to know how to solve this problem. If you can write the dissociation and the Ka expression, you've gotten 1 mark. Ooh, maybe out of 4. That's a quarter of your marks. Pretty nice. Now, whenever you're given a quantity in a question, like this one, do you remember when we talked about our 0.1 molar HCl? Did that refer to our initial concentration of HCl, or did that refer to the concentration of HCl that's actually in the solution? That's our initial concentration, because really, how much HCl is there together? There's none of it, right? It's all dissociated, right? How much do we really have of this? 0%, right? Why is my pen not switching? There we go. Keep trying to draw. We have 0% of HCl, but we still say it's 0.1 molar HCl because it's useful to say that. As a chemist, I know if you say 0.1 molar HCl, you mean that you took 0.1 mole of HCl, you put it in 1 liter, and because I'm a chemist, I know that it's completely dissociated. And it's okay to write 0.1 molar HCl, even though there isn't really any HCl at all. Yes, it's all H plus and Cl minus, but we still write it that way. And the same thing applies with weak acids. So this 0.5 molar CH3COOH, the concentration you're given in the question is always the initial concentration, okay? Because it's easy to calculate. You say, I put this many moles in this liters, and you get your concentration. To find the actual concentration of the acid, you would have to do a rice table and nonsense like that. And who wants to do that just to write a concentration on a bottle, right? That's ridiculous. So the concentration given in the question, concentration of acid given in the question, is always the initial. So it's not going to be the equilibrium concentration. It's always going to be the initial concentration. When it comes to a COOH kind of acid, which hydrogen is the acidic hydrogen? Which is the hydrogen that comes off? Is it the yellow hydrogens, or is it the green hydrogen? It's the green hydrogen. Okay, so just remember that when you have a COOH acid, the yellow hydrogens will never come off. It's only that one. Okay, so now we say, all right, this is great. We know our initial concentration. We have our reaction, and so now we're going to set up a rice table. We know our initial concentration because it was given in the question. Hello, here we go, 0.50 molar, okay? Now, initially when we dump that stuff into water, how much is dissociated in that instant we put it in? Technically, none of it, Okay, we're talking like just in that one little instant, a nanosecond later, and it will be dissociated, but we're talking like in that instant, okay? So always your initial concentrations of the dissociated ions is always 0. So the initial concentration of the dissociated ions is always equal to 0. Because those are 0, which way does this equilibrium have to shift? Has to shift to the, if I've got none of this, it has to shift to the right, because I cannot make stuff on the left if I've got nothing on the right. Yes? So that means these are going to be going up. So these are always going to be positive, because you cannot go down from 0 molar. Yeah? And this is always going to be negative. And so we get 0.50 minus x, and we get x, and we get x, and those are our equilibrium concentrations. Okay, so we have our equilibrium concentrations. We're going to make sure we have written our Ka expression, including Ka equals, don't forget that part. I don't know, sometimes people forget that. Ka equals products of reactants, write your actual substances in there. And then, where did we get this number from? The 1.8 times 10 to the minus 5. That's from the data booklet. That's our Ka value. And then we get these come from the E in the race table. Now, I don't know about you, but I look at this and I say, got an x squared term, got an x term, got a number. That means I have a quadratic. Ugh, I don't want to do a quadratic. Do you want to do a quadratic? Probably not. Some of you like to. You've got a calculator function that'll do it for you. But back in the equilibrium unit, usually we had a squared term over a squared term. Yes, and we could just take the square root of both sides. Can we do that here? No, we cannot. But what do you remember about weak acids? How much of them is dissociated compared with how much is still together? Not much. That means that the x value is very small. Yes? So how big do you think it is compared with 0.50? It's very small compared to 0.50. So what we're going to do is we are going to write the following. We're going to write assume x is insignificant. That means that x is too small to matter. And that'll get rid of the x term. And then we can just be like, oh, hey, now I've only got an x squared term and I can just do normal algebra on that. Okay? So let's just take a little look at a few things here. In order to get full credit for doing that, you actually need to, you have to write the assumption. So you must write the assumption. Assume X is insignificant. You need to point an arrow at the X that you are assuming is insignificant, because if you just write over on the side somewhere, assume X is insignificant, you could be referring to the green X. Like if you didn't have an arrow pointing to it, right? Is the green X insignificant? No. The blue X, let me grab blue. The blue X is insignificant because it is much, much smaller than 0.5. Yes? And in fact, that's another way of writing the assumption if you want to. You could say assume X is much, much less than, two less than signs, 0.50. That's another way of writing it, if you prefer not to write assume X is insignificant. Either way will work. This assumption is worth 0.5 marks. You will lose 0.25 if you don't have an arrow pointing to the X you are talking about. Yes? It will be minus 0.5 if you are not clear in what you mean. So if you write assume insignificant without mentioning what is insignificant, you will not get credit for that. Does that make sense? So you have to assume X is insignificant. Yes? All right. Now, if you think I'm crazy and very picky and all that stuff, back in the day, back when we had like more contact with the university, we were actually told by the professors up there that, oh, Burnaby Mountain students are very good because when they come here, they know how to show their work. So I'm going to keep insisting on things like this because apparently Burnaby Mountain students know how to show their work. Okay, so there we go. Anyway, that leaves us, if we get rid of that X term, we have 1.8 times 10 to the minus 5 equals X squared over 0.5. We'll take the 0.5 and move it up here. Then we will multiply these two guys and get 9.0 times 10 to the minus 6 is equal to X squared. And then we will take the square root of both sides. And there's a typo here. The root of 9 times 10 to the minus 6 is 3 times 10 to the minus 3. Okay, so that's a typo there. It's not 3 times 10 to the minus 6. It's 3 times 10 to the minus 3. And I need to fix that. As always, when we get to the end of the question and we find an X value, we need to go back and say, what was the question asking for? What the heck is X? So here's our question. I just copied it here. It's asking, what is the H plus concentration? And what the heck was X? How handy. X is the H plus concentration. So we're good. So we can just say that concentration of H plus is equal to X is equal to 3 times 10 to the minus 3 molar. Okay, so again, I need to fix that. Is good? Okay. Now, just to prove to you that X was indeed insignificant, okay, if we had calculated the question and used the quadratic formula, instead of 3 times 10 to the minus 3, we would have gotten 2.99 times 10 to the minus 3, yes? So our initial concentration was 0.5 molar. Our change in concentration was 0.00299. And so our equilibrium concentration would be 0.49701. But if we round that to 2 sig figs, what do we get? 0.50. And what was our initial concentration? 0.50. So was our change insignificant compared with 0.50? Yes, it was. Now, if you are in university, you should take your X value and see if it is indeed insignificant compared with your original value. And if it's not, you'll need to do a quadratic. But in Chem 12, you can just always make that assumption, okay? Now, another way to look at it is this value actually any different from 0.030? If we go to sig figs, 2 sig figs, what does that round to? That rounds to 0.0030, which is, guess what we got using the assumption. Yes? So either way, you can prove that it's insignificant. All right. You don't need to be able to do that calculation or prove it. It's just there so you feel better about it. We are not going to go through this example in gory detail because it is exactly like the last one, but we're just going to go through and point out a few things. Okay, first of all, what's the first thing you should ask yourself when you are asked what is the pH of blah 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 benzoic acid? Tell your partner, what's the first thing you should ask yourself? Yep, you should ask yourself, is it weak or is it strong? And go look up benzoic acid and tell me, which one do we have? It is weak. And then once you have determined it is weak, what do you know you should use? You should use a rice, and not just rice, but also Ka. Okay, so we're going to use rice and Ka. Rice and Ka. Excellent. And what do you know about this 3.0 molar? What row of the rice table does it go in? That is our initial. And what are the dissociated ion concentrations initially? They are 0. And then, of course, we do plus x, minus x. And just so you know, you can make the assumption up in the rice table if you want to. That saves you having to write the x in your substituted Ka. Don't forget, you need to write your Ka first, the expression with the concentrations. Don't just go throwing in the x's and stuff. So you can either write your assumption there or you can plug it in and have your assumption down here. Either way is fine, but if you do it up here, you can skip straight to this one. Yes? So if you make that assumption, you don't have to put the x in there. You can skip straight to here. Solve for x squared. Solve for x. We get the hydrogen ion concentration, 1.4 times 10 to the minus 2. You would show your pH formula, negative log of hydrogen, negative log of 1.4 times 10 to the minus 2. And don't forget, what's different about sig figs for pHs?
Add one additional sig fig.
No. Something like that. Only digits after the decimal count. So if you had 10.36, it would just be the 36. Okay, so if you have a pH equal to 10.36, it has 2 sig figs. In any p-value, so that could be pH, POH, PKW. Only digits after the decimal are significant. Now, if it's not a p-value, just go with your normal rules. Forget about all this like after the decimal nonsense. So if I give you hydrogen ion concentration, just do normal sig figs, okay? It's only p-values because they have had a log taken, okay? And that number in front of the decimal is the exponent. And the exponent is not part of your sig figs, okay? So here we have 2 sig figs, which means over here we need to have 2 sig figs, which are the 2 after the decimal. Okay? All right, so here's a list of steps if you're using Ka and H+. So this is for a weak acid. Remember to make a correct Rice table. Okay, including the ionization equation of the weak acid. Remember to write the assumption X is insignificant. Remember to point an arrow at the X that is insignificant. Remember to write the Ka expression. That's with your concentration square brackety things. And then plug in everything from the E line in the Rice table into the Ka expression. The rest of the marks will be assigned for solving for X correctly and calculating anything else like pH that you're asked to calculate. Okay? Now, here we have some questions. Oh, that's okay. I asked people to do numbers 1 through 9 in my other block, so I'm going to ask you guys to do numbers 1 through 9. Now, some of these are acids and some are bases. For all of them, you're going to be calculating the hydrogen ion concentration, the hydroxide ion concentration, the pH, and the pOH. This is going to help you remember how to do things for your quiz on Friday. Oh, by the way, I would like to have your test next Thursday. Okay, and we will not have time to do a Ka quiz. So what I will do is I will send you with a practice quiz over the weekend. Yes? Monday, we're going to do a lab. So we're going to learn how to do a titration, learn how to do the math around a titration. You should already know the math, but we'll review it. And then we'll do a lab on Monday because it's a long block day. Okay? So I will send you home with the review package over the weekend for your test, which is next Thursday. Yes?
If I use long block, is it
1-3, and then 2-4 is on Tuesday.
Not 2-4.
I think so. I'm pretty sure. Yeah, 2-4 is on Tuesday. Yeah. So we would be on Tuesday. We're on Tuesday, so I would not see you Monday. Okay. I keep getting confused. One of the many reasons I don't like long blocks, but I do like them for doing labs in Chem 12. So if we only have them once in a while, it's okay. Yeah. All right. So because of the fire drill, this is as far as I got with my other blocks. So if you guys just want to work on this now, go for it. Okay.
Yeah.
So page 95. Number 1 through 9. Oh, I wanted to mention something. These guys here. Doesn't that look scary?
Yeah.
Yes. And you say, oh my gosh, what is that? What do I do with it? It's okay. Do not panic, because what I want you to notice is I want you to notice that we have 6 waters and it's attached to a chromium. And here we have 6 waters and it's attached to an aluminum. And when I say don't panic, I really mean don't panic, because let's go to our data pages. And let's see what we can find on our data pages. Look what we have right here. We have 6 waters attached to an aluminum. And so if you don't know how to write a dissociation equation, it doesn't matter, because it does it for you. Yes? Now, what I want you to take a look at here, it's not actually as bad as it looks. You start with 6 waters on the left-hand side. On the right-hand side, you end up with 5 waters. One of the waters lost a hydrogen and became an OH. Okay? So that's why it works, but you don't have to worry about it because it's written there. Yes? So you can just be like, oh, it's fine. I can just look it up. And how do you find these without having to search for them too hard? Oh, it's all the really long names, right? Long name, long name, long name. We have the hexa 6 aquo water aluminum ion. And we have the hexa 6 aquo water chromium ion. And we have the hexa aquo iron ion. Okay, so when you see them, don't panic. Just remember, go look at your data booklet and you'll be fine. Okay, so page 95, numbers 1 through 9. That's not the right one. There we go. Does it actually tell
$15, yes, which is what I
seriously, for $15, that's amazing. Yes, of course. So every question you need to ask yourself, is it an acid or is it a base? Is it strong or is it weak? Acid or base, strong or weak? Wow. And you probably don't have enough room to do all the work on that little page unless it's a strong one. So get yourself some paper. There's lots of free paper back here. If you like, help yourself. And there's still apples if you want an apple. Yes. Yeah, you can just assume they're all aqueous for now. I don't believe what else. Yeah. It'll become important when we're doing solubility, but with this one,
Yeah. I want to. Yeah.
okay, I'm gonna close this so I can take attendance.
Oh,